Welcome to Dart Tutors. Today, we'll be diving into some advanced techniques for solving differential equations, a key topic in IB mathematics analysis and approaches higher level. By the end of this video, you will be able to solve homogeneous differential equations using a specific substitution, solve first-order linear differential equations using an integrating factor, and approximate solutions using Maclaurin series. These methods are powerful tools for tackling a wide range of problems, from population growth to physics. Let's begin with homogeneous differential equations. Our goal here is to learn how to identify and solve the specific type of equation. A first-order differential equation is called homogeneous if it can be written in the form dix equals f of y over x. This means that the right-hand side of the equation is a function of the ratio y over x. This structure is the key to solving them. The method involves a clever substitution. We let y equal v times x, where a v is a new function of x. This substitution will transform the original equation into a separable one, which we already know how to solve. First, we need to find an expression for dx in terms of v and x. Using the product rule on y equals vx, we get dx equals v plus x times dv dx. Now we substitute both y equals vx and our new expression for dx into the original homogeneous equation. This gives us v plus x times dv dx equals f of v. Notice how the x's have canceled out on the right-hand side. Rearranging this equation, we get 1 over f of v minus v times dv dx equals 1 over x. This is a separable differential equation, which we can solve by integrating both sides. Let's see this in action with an example. Let's work through an example to solidify this method. We'll solve the differential equation dx equals x plus 2y all over x. First, we need to show that this equation is homogeneous. We can rewrite the right-hand side as 1 plus 2 times y over x. Since it's a function of y over x, it is indeed homogeneous. Now we apply our substitution. We let y equal vx, which means dx is v plus x times dv. Next, we rearrange the equation to separate the variables v and x. Subtracting v from both sides gives x times dv dx equals 1 plus v. Then we separate the variables to get 1 over 1 plus v times dv equals 1 over x times dx. Now we integrate both sides. The integral of 1 over 1 plus v is the natural logarithm of the absolute value of 1 plus vi. The integral of 1 over x is the natural logarithm of the absolute value of x. We add a constant of integration. To simplify, we can write the constant c as the natural logarithm of some constant a. Using logarithm properties, we combine the terms on the right to get ln of a times x. Exponentiating both sides gives 1 plus v equals a times x. Finally, we substitute back v equals y over x to get y over x plus 1 equals x. Multiplying by x gives our general solution, y equals x squared minus x. This is the general solution. If we were given an initial condition, we could find the specific value of a to get a particular solution. Now, let's move on to another powerful technique, the integrating factor method. This method is used to solve a specific type of first-order linear differential equation. The standard form for these equations is dx plus p of x times y equals q of x. Here p of x and q of x are functions of x only. The key idea is to multiply the entire equation by a special function called the integrating factor, which makes the left-hand side the derivative of a product. The integrating factor, which we'll call I of x, is given by the formula e to the power of the integral of p of x dx. We don't need a constant of integration here. Let's see the steps for solving an equation using this method. First, ensure your equation is in the standard form. Second, calculate the integrating factor using the formula. Third, multiply every term in the equation by this integrating factor. Fourth, the left-hand side will simplify to the derivative of the product of the integrating factor and y. Fifth, integrate both sides with respect to x to solve for y. This method is particularly useful when the equation is not separable. Let's apply the integrating factor method to solve the equation di to dx plus 3x squared y equals 6 squared. First, we identify p of x and q of x. The equation is already in standard form, so p of x is 3x squared and q of x is 6x squared. Next, we calculate the integrating factor. We integrate p of x, which is 3x squared, to get x cubed. So the integrating factor I of x is e to the power of x cubed. Now we multiply the entire differential equation by e to the x cubed. This gives us e to the x cubed times di dx plus 3x squared e to the x cubed times y equals 6x squared e to the x cubed. The left-hand side is now the derivative of the product y times e to the x cubed. This is the magic of the integrating factor. So we have d dx of y times e to the x cubed equals 6 squared e to the x cubed. To solve for y, we integrate both sides with respect to x. The integral of the left side is simply y times e to the x cubed. For the right side, we can use a u substitution, letting u equal x cubed. The integral becomes 2 times e to the x cubed, plus a constant c. Finally, we divide by e to the x cubed to isolate y. This gives us the general solution. Y equals 2 plus c times e to the negative x cubed. This is the general solution to the differential equation. Again, an initial condition would allow us to find the specific value of c. Our final topic is using Maclaurin series to approximate solutions to differential equations. This is a powerful technique when an exact solution is difficult or impossible to find. The goal is to find the first few terms of the Maclaurin series for the solution y of x, given a differential equation and an initial condition at x equals 0. Recall the Maclaurin series formula. It's an infinite polynomial where the coefficients are determined by the derivatives of the function evaluated at x equals 0. The strategy is to use the given differential equation and initial condition to find the values of these derivatives at x equals 0. First, we use the initial condition to find y of 0. Second, we use the differential equation to find y prime of 0. Third, we differentiate the differential equation to find I double prime and then evaluate it at 0. We continue this process to find as many derivatives as needed for the desired number of terms in our approximation. Let's see how this works with an example. Consider the differential equation di dx equals x minus 4xy, with the initial condition y of 0 equals 1. We want to find the first 3 non-zero terms of the Maclaurin series for y. First, we have the initial condition, so y of 0 is 1. Next, we find y prime of 0. We substitute x equals 0 and y equals 1 into the differential equation. This gives y prime of 0 equals 0. Since y prime of 0 is 0, the x term in the Maclaurin series is 0. We need to find the next non-zero term. We differentiate e prime of x using the product rule to find y double prime of x. Then we substitute x equals 0, y equals 1, and y prime of 0 equals 0. This gives y double prime of 0 equals negative 3. Now we have a non-zero term. The second term in our Maclaurin polynomial is y double prime of 0 over 2 factorial times x squared, which is negative 3 over 2 factorial times x squared. We need one more non-zero term. Let's find the third derivative. We differentiate I double prime of x to find y triple prime of x. Then we substitute x equals 0, y equals 1, y prime of 0 equals 0, and y double prime of 0 equals negative 3. This gives y triple prime of 0 equals 0. Again, the term is 0. We must continue to the fourth derivative. Differentiating a triple prime of x gives y quadruple prime of x. Substituting our known values gives y quadruple prime of 0 equals 36. Now we have our third non-zero term. It's y quadruple prime of 0 over 4 factorial times x to the fourth, which is 36 over 4 factorial times x to the fourth. Putting it all together, the first 3 non-zero terms of the Maclaurin polynomial for y are 1 minus 3 over 2 factorial x squared and plus 36 over 4 factorial x to the fourth. This simplifies to 1 minus 3 halves x squared plus 3 halves x to the fourth. This polynomial provides a good approximation of the solution y of x near x equals 0. Let's quickly recap what we've covered. We've explored three essential methods for solving and approximating differential equations. First, we learned how to solve homogeneous differential equations by using the substitution y equals vx to transform them into separable equations. Second, we mastered the integrating factor method for solving first-order linear equations of the form dx plus p of xy equals q of x. Third, we saw how to use Maclaurin series to find polynomial approximations of solutions, which is crucial when an exact solution is not feasible. These techniques are fundamental for IBAAHL and will be invaluable in your studies. Now let's test your understanding with some practice questions. Here are 5 practice questions designed to reflect the style and difficulty of IBAAHL assessments. Take your time to work through them. Question 1. Solve the homogeneous differential equation dx equals x plus y all over x, given the initial condition y of 1 equals 2. Question 2. Solve the first-order linear differential equation ddx plus 2y equals e to the negative x. Question 3. Consider the differential equation dx equals x squared plus y squared, with y of 0 equals 1. Find the first 3 non-zero terms of the Maclaurin series for y. Question 4. A population P grows according to the logistic model dpp dt equals 0.02p times 1 minus p over 1,000. If the initial population is 100, find the population after 50 years. Question 5. Solve the differential equation x times dx plus y equals x times cosine of x, given y of pi over 2 equals 0. Pause the video here and try to solve these on your own. When you're ready, continue for the fully worked solutions. Welcome back. Let's go through the solutions together. For question 1, we have a homogeneous equation. We substitute y equals vx and dx equals v plus x dv dx. After separating variables and integrating, we get ln of v equals ln of x plus c. Substituting back and using the initial condition y of 1 equals 2, we find c equals ln of 2. The particular solution is y equals 2x. For question 2, we use the integrating factor method. P of x is 2, so the integrating factor is e to the 2x. Multiplying the equation by e to the 2x and integrating gives y times e to the 2x equals e to the x plus c. The general solution is y equals e to the negative x plus c times e to the negative 2x. For question 3, we find the Maclaurin series. We have y of 0 equals 1. Y prime of 0 is 1. Y double prime of 0 is 2. Y triple prime of 0 is 6. The first 3 non-zero terms are 1, x, and x squared. This is the start of the series for e to the x. Question 4 is a logistic equation. We separate variables and use partial fractions to integrate. After solving for p and applying the initial condition, we find the particular solution. Plugging in t equals 50, we find the population is approximately 269. Finally, for question 5, we first rewrite the equation in standard form. The integrating factor is x. Multiplying and integrating gives xy equals x times sine of x plus cosine of x plus c. Using the initial condition, we find c equals 0. The particular solution is y equals sine of x plus cosine of x all over x. I hope this video has helped you deepen your understanding of these advanced differential equation techniques. Keep practicing, and you'll master them in no time. Thank you for watching.